In this chapter, we'll briefly survey organic polymers. And by organic polymers, we mean synthetic polymers. There are naturally occurring polymers, but there are also organic compounds. Examples would be nucleic acids or various polysaccharides, various polymeric carbohydrates. But those polymers are usually covered in different courses such as biochemistry and chemistry of natural products. In an organic chemistry course, when we talk about organic polymers, we mean synthetic organic polymers. And we'll only briefly review them. We'll review their structure, classification, synthesis, and properties of organic polymers. We classify organic polymers either according to structure or according to type of polymerization. According to structure, there are two large groups of polymers, linear and branched. Linear, of course, as name indicates, are long chains, long polymeric straight chains without any branching. Those chains obviously coil a lot and interact with each other through intermolecular interactions. Branched polymers are rather diverse, and there is a very large number of different types of branched polymers. So here are some typical branched polymers provided in this square. So these type of polymers are kind of tree-like polymers, typical branching just like a tree. Sometimes they are called arborols. Then another type of polymer is branching from a single point. So those would be star polymers. And finally, third type is polymer that has a straight chain and then branches are branching off that straight chain. Those are comb-like polymers. Finally, another type of polymer that is also branched polymer is cross-linked polymer. In that case, individual straight chains are cross-linked with very short cross-links that connect those individual chains. More common classification is according to type of polymerization. And we have two basic types of polymerization: addition polymerization, which we'll be covering now, and condensation, which we'll cover a little bit later in this chapter. So addition polymerization could be free radical addition or ionic. And in turn, ionic could be either cationic or anionic polymerization. And as I just mentioned, another different type of polymerization is condensation polymerization. So free radical polymerization involves polymerization of alkene. So alkene is monomer. So alkene reacts with free radical initiator. So we add compound that typically upon heating breaks up and gives individual free radicals. Often such compound is some peroxide. And then that free radical initiates polymerization of an alkene. And it should be mentioned that air itself naturally contains free radicals. So often when various alkenes are left exposed to air, they will spontaneously polymerize because those free radicals from air will cause polymerization. So polymer adds to an alkene, simply free radical addition, which we have covered earlier. So here is in amber square free radical initiator. And that gives new free radical. So upon addition, now we have new free radical, which is carbon radical. And now that carbon radical adds to another molecule of alkene, and so on, and chain keeps growing. We add only very few molecules of initiator, and that results in formation of or growing of large number of polymeric chains, or actually few chains keep growing. We can, to an extent, manipulate size of the chain and distribution of the chain lengths by manipulating the amount of the radical initiator that we add. You can see that this reaction results in conversion of carbon-carbon pi bond into carbon-carbon sigma bond. So much more stable bond. So these processes are highly exothermic, and actually a reaction could run out of control and become explosive if it's not controlled. So we have to control temperature really carefully. So typical such reaction releases 20 kilocalories per mole. That's quite a lot, highly exothermic, and we have to usually carry out this reaction with cooling. Upon completion of the reaction, when all of the reactants are used up, Then free radicals undergo termination reaction, and reaction spontaneously terminates on its own to give termination products. A little bit different type of polymerization is ionic polymerization. Ionic could be cationic, where we add cation, so some strong organic cation. And that cation, basically what it means, strong organic cation, that means highly electron deficient species. And that cation or electrophile, typically very strong Lewis acid, adds to carbon-carbon double bond to form bond to carbon and results in formation of carbocation. That carbocation adds to another molecule of alkene, and that's how reaction keeps propagating. That's how chain keeps propagating. What is interesting in this case is that once all of the reactants are used up, the reaction actually doesn't stop. We have to add some reagent, water or something else, to react with this intermediate carbocation to stop the reaction. So such polymers are called living polymers, because after reactants are used up, these chains are still so-called living. And we could add another different type of monomer and then generate another segment of the chain with a different type of monomer and so on. So this is much more useful, but also much more expensive way to carry out polymerization, living polymerization or ionic polymerization. And also, in this case, chain length compared to free radical polymerization is more or less uniform. We get what we call monodispersed polymers. All of the chains have about the same length, while in case of free radical polymerization, we get a distribution that is more like a normal distribution, like a bell curve. Related type of polymerization is anionic polymerization. In this case, we add some very strong nucleophile, like let's say butyl lithium or methyl lithium, some nucleophile that will add to carbon-carbon double bond. That addition results in formation of new carbanion, and then that carbanion adds to another molecule of alkene, and chain propagates that way. So it's analogous to cationic polymerization. Just like cationic polymerization, polymers that are obtained are monodisperse, all of them have about the same chain length, and it's living polymerization, which means we have to quench reaction at the end by adding either water or dilute acid, or we can form a copolymer. That means add a different type of monomer and keep on doing the reaction by adding different types of polymers until we get polymer with desired properties. Here are some examples of polymers. Typically, in industry, we carry out free radical polymerization. It's much less expensive, and typically polymers that are obtained are of satisfactory quality. And of course, in industry, we are very concerned with the cost. So on the left are monomers, monomeric molecules, and on the right are polymers. So you can see how polymers are designated, both as a formula and the nomenclature. So nomenclature is poly and then trivial name of the monomer. So on the left we have vinyl chloride in the first example, and so the name is polyvinyl chloride. When monomer is complex name, that means it's composed of two or more words, typically complex would be two words, then we place name of monomer in parentheses. So it's polyvinyl chloride. Abbreviation is PVC. In this case, we have tetrafluoroethylene, that's one word, so we would name this polytetrafluoroethylene. In this case, prefix poly is simply placed before the name of the monomer. This also goes under trade name of Teflon. Polytetrafluoroethylene is also frequently abbreviated as PTFE. And then this polymer is, or monomer, to start first with monomer, it's methyl methacrylate. And so polymer is polymethyl methacrylate. That one has glass-like properties, and it's sold under trade names as lucite or plexiglass. As I already mentioned, polymerization of some alkenes is spontaneous. That's because air naturally contains free radicals, and those free radicals from air, if alkene is exposed to air, will catalyze or start free radical chain and will catalyze polymerization. And so if left standing in air for some amount of time, alkene may polymerize. So here we have a bottle of styrene. Styrene is a liquid. It is compound, you will see formula in a minute, that has phenyl group and vinyl group attached to it. so styrene is a trivial name for vinyl benzene. It easily polymerizes in air, and in fact this is how polymerization reaction was discovered in the first place. Because chemists in the 19th century noticed that styrene, when left standing, would actually polymerize into a solid. So what should be a liquid became a solid, and upon analysis they stumbled upon polymerization reaction. So this is how reaction works. So styrene on its own, left on its own, simply due to free radicals present in the air, polymerizes to give long chains of polystyrene. pH, of course, is an abbreviation for phenyl group. And in fact, this bottle of styrene has already polymerized. It has been kept around for a while. It wasn't stored properly. It should have been stored in a sealed bottle in a freezer. That was not the case, and this bottle has polymerized. We know that it has polymerized because if we open the bottle and tilt it on its side, nothing comes out. It's filled with solid. Another important reaction in preparation of polymers is crosslinking. Crosslinking makes polymers much harder. That's because chains cannot slip past each other, so polymers become much harder, and their melting or softening point also becomes higher. To achieve crosslinking in polymers, we add a small amount of crosslinking agent. How much will depend on desired properties of the polymer. The more crosslinking agent we add, harder or more brittle polymer will become, and its melting or softening point will become higher. So in this case, let's say we want to polymerize styrene, we will add cross-linking agent. Cross-linking agent is a bifunctional compound. So we are polymerizing styrene, and then cross-linking agent in this blue box is a bifunctional compound. It means it has two functional groups. And so one functional group in the course of polymerization is incorporated in one chain, and the other functional group is incorporated into the other chain. And that way it cross-links or connects the two chains. So one molecule becomes part of the two chains. It cross-links two chains. So that's how cross-linking occurs. In this case, we have two cross-linking points, two cross-linking bridges. The more of them, as I said, we have, the more difficult it is for chains to slide past each other, and molecule or polymer becomes more brittle and more rigid. Fewer cross-linking molecules are added, and then the polymer will become softer, or will end up being softer. Another type of reaction that is common in preparation of polymers is condensation reaction. We covered condensation reactions earlier in the previous chapter when we were looking at aldol condensation. So you know that condensation is a reaction where formation of organic molecule is accompanied by evolution of a small molecule. Typically that small molecule is something like water or small alcohol like methanol or ethanol, and since condensation reaction was or is usually carried out with heating, then that molecule will boil out and condense, and that byproduct would then condense out and we would discard it. And that's why it's called condensation, because byproduct condenses out of the reaction. Besides aldol condensation, reactions such as esterification are also considered to be condensation reactions. So polyesters are prepared in condensation reactions. Now, unlike ordinary esterification, where reaction is a reaction of alcohol and, let's say, carboxylic acid in Fischer esterification, or maybe ester and alcohol in trans-esterification reaction, now we need bifunctional compounds. In order for chain to form, both dicarboxylic acid and dialcohol or alcohol have to be bifunctional. So we need dicarboxylic acid and a diol. Or alternatively, if we want to carry out trans-esterification reaction, which is more commonly carried out in industry, then we need diester and diol. So here is one example. This particular diester is dimethyl terephthalate, and dialcohol, diol, is ethylene glycol. That's actually a component of antifreeze. And so they react in such a way that they form new ester bonds. It's trans-esterification reaction where methyl group leaves and is replaced by ethylene glycol group. So you can see how chain is formed, and parts of the chain in yellow that come from the original ester or dicarboxylic acid and parts that come from diol. This particular polyester is sold under the trade name of Dacron or Mylar. Another type of condensation reaction, esterification reaction, is formation of polycarbonates. In this case, we use diol, bisphenol A, that's particular one. Polycarbonates are solid, rigid polymers, and to do that we need monomers that are themselves rigid molecules, which means we can't have too many sp3 carbons. We can't have many possibilities for bond rotation. We need molecule that is flat, that is rigid, where there is not much possibility for movement, for bond rotation, which means a lot of sp2 carbons. Bisphenol A is named as bisphenol A because it's made out of two molecules of phenol. That's why it's bis. That's Greek prefix for twice or two times. So bisphenol, two molecules of phenol, and you can recognize molecules of phenol here. And A, that's not obvious. A stands for acetone. So the middle part of the molecule, those three carbons come from acetone. So reaction of phenol and acetone gives bisphenol A. That's our diol, very rigid diol, unlike ethylene glycol, which is very flexible, has very flexible chain. And then we react that with diphenyl ester of carbonic acid, diphenyl carbonate. Of course, carbonic acid itself is unstable. We cannot use it. We could use something like phosgene, dichloride of carbonic acid, but as you probably know, phosgene is highly toxic. So we use diphenyl carbonate. Diphenyl carbonate has phenoxy groups, and we have encountered that in the previous chapter also. Phenoxy groups are very good leading groups. So reaction of these two gives very good glass-like polymer. In fact, that's excellent polymer because its optical properties are very similar to that of glass. So and it's much lighter than glass. So, and also when it breaks, it doesn't produce sharp edges like glass. So those properties, that it's safe when it breaks. It also has very high resistance to breaking, higher than glass, and optical properties similar to those of glass, and being very light, make it very suitable for making things such as eyeglasses and also windshields for cars. And here are parts of the molecule in yellow that come from bisphenol A and in blue from dimethyl carbonate. So that's polycarbonate. One of the trade names for polycarbonate is Lexan. Then another type of polymers that are very strong are polyamides. Of course, those are polymers that contain amide bond. Polyamides could be prepared from dicarboxylic acid, like adipic acid, and diamine, like 1,6-hexanediamine. And then we end up with polymer. Again, here are parts from dicarboxylic acid and from amide. Those polymers are called nylons. And nylons are designated with numbers. In this case, we have nylon 6,6. So first number indicates number of carbon atoms in dicarboxylic acid, and second, number of carbon atoms in amine. So nylon 6,6. Of course, we could make other nylons like nylon 6,4, nylon 4,4, and so on. Another type of nylon that we can prepare is prepared from amino acid, because amino acid is bifunctional and, of course, can form a polymer. Such amino acids are usually prepared by ring opening of corresponding lactam. So we use lactam as starting material. We carry out ring opening with a base, and that produces carboxylate anion, so amine and carboxylate anion. And upon addition of water and heating, this will polymerize into nylon polymer. Since this nylon polymer contains only one monomer, then it's designated with a single number. So this is nylon 6 because starting monomer contained only 6 carbon atoms. Nylon is very strong polymer. So nylon is polyamide, and polyamides are much stronger compared to polyesters. So their fibers, both polyamides and polyesters are fibers. And since those fibers are much stronger, we have already seen that polycarbonate has rather good desired properties as replacement for glass. It's glass-like polymer. But it would be really nice if we could make a polymer like polycarbonate that is also much stronger. And of course, we can do that by making corresponding polyamide. So then we will use aromatic diamide, so very rigid aromatic diamine, not diamide, aromatic diamine, so very rigid amine, and aromatic dicarboxylic acid, rigid dicarboxylic acid. And when we polymerize the two, you can see parts of the molecule that originate in yellow from diamine and in blue from dicarboxylic acid. Then this polymer is sold under the trade name of Kevlar. It's very strong, it's resistant to impact, and it's used in making bulletproof vests. Then the final type of polymers are polyurethanes, also very useful polymers with broad range of applications. First, we will not cover urethanes in this course. They are derivatives of carbamic acid. So this is carbamic acid. It has carbonyl group and two substituents on the carbonyl group. One substituent is amide substituent and the other substituent is hydroxide. Of course, carbamic ester would be alkoxide substituent, OR substituent. And those actually esters of carbamic acid are called urethanes. Now they are prepared in reaction of an isocyanate, highly toxic compound, with an alcohol. So reaction of alcohol, addition of alcohol to a carbonyl group of isocyanate results eventually in formation of urethane. These compounds would be rather expensive if we were to make polymers that would contain a bifunctional urethane chains, if they were made only of bifunctional urethane chains. So we add what are called spacers, and spacer is polyethylene glycol. Simply we can take ethylene glycol, rather inexpensive alcohol, and polymerize it under acidic conditions to polyethylene glycol chain of desired length. We can make polyethylene glycols of particular length, 100, 200, 400. Those numbers refer to molecular weight. And then we react diisocyanate with polyethylene glycol. So in this case, polyethylene glycol is already a polymer, but it plays the role of a monomer. And that results in formation of polyurethanes. Polyurethanes have a number of uses. They could be used to make fibers. They could be used to make things like sponges or furniture, because as polyurethanes are made, we can bubble gas through it, like carbon dioxide, and they will make very nice spongy compounds. So they could be used in making, for example, cushions for furniture. And we have reached the end of the chapter on polymers. And not only that, but we have reached the end of the course. And that being the end of the course, the only thing that is left is to wish you good luck on the final exam.